A Toyota Corolla, 380,000 miles. Original engine, never rebuilt. The owner just changes the oil. That is it. This is not luck. This is not a coincidence. This is deliberate engineering. When Ford, Chevrolet, and Honda finally understood what Toyota had built, they panicked. In the next 20 minutes, I will show you exactly how Toyota did it, and the one decision made in the 1960s that changed everything. Let us get into it. It starts in 1966, not at a press event, in an engineering meeting at Toyota's technical center in Japan, where engineers were asked one question. How do you build an engine for someone who will never maintain it properly? That question sounds simple. It is not. And in 1966, nobody else was asking it. Ford wanted cheap and fast. Chevrolet wanted displacement. Honda wanted technical prestige. Toyota asked something different. What happens when a farmer in rural Japan buys this car, skips every service interval, uses whatever oil is available, and still expects it to start every morning? That question produced a different engine. The first Corolla launched with a 1.1-liter four-cylinder that was unremarkable on paper. But underneath, every decision was built around one priority: survive abuse, wider bearing clearances, an over-engineered cooling system, a simplified valve train. Every unnecessary component was eliminated. It was not glamorous engineering, but it produced something nobody else was building: an engine that could take punishment and keep running. The Corolla sold 1.1 million units in 3 years. Not because it was fast, because it started every morning. And Toyota had only just begun. Here's the shorter version. By 1980, Toyota had been refining the Corolla engine for 15 years. The 3AU looked ordinary on paper, a basic one, 5-liter four-cylinder, no exotic technology. But then the fleet data started coming in. Taxi companies and rental fleets are the harshest environment any engine will ever face. Irregular maintenance, multiple drivers, oil changes that happen late. Engines pushed hard from a cold start every single day. In these conditions, most engines of that era were showing serious wear by 150,000 miles. Head gasket failures, oil consumption, ring wear. Toyota Corollas in Japanese taxi fleets were hitting 250,000 miles in the same conditions. And the engines were not worn out. They were just running. When Ford's fleet customers started asking why the competition's cars lasted longer, and when Chevrolet's engineers had to answer the same question, the discomfort was real. Honda's reaction was different. Honda prided itself on engineering excellence. The idea that Toyota, which Honda privately viewed as a manufacturing company, not an engineering company, was producing more durable engines, forced an honest internal reckoning. It directly influenced Honda's own VTEC development, but none of them had fully understood how Toyota was doing it. They could see the outcomes. They could not reverse engineer the philosophy. In 1987, Toyota introduced the 4AFE. This is the engine historians point to as the moment the Corolla went from impressive to legendary. On paper, it looked ordinary. A 1.6-liter twin-cam, 1.6-valve four-cylinder. Similar specs to the Honda Civic and Ford Escort. Same displacement. Similar power. What you could not see on the spec sheet was the internal geometry. Toyota engineered the 4AFE's bore and stroke ratio not for maximum power, but for minimum stress at everyday driving RPM. Most people drive between 1,500 and 3,500 revolutions per minute. In that range, this engine was barely working, and piston speed at common RPM is the single most important variable in long-term wear. The difference between a high-stress design and a low-stress design, over 200,000 miles, is not marginal. It is the difference between an engine that is tired at 150,000 miles and one that is just getting started. Toyota also used a timing chain instead of a rubber belt. Many competitors required belt replacements every 60,000 to 90,000 miles. A missed replacement could destroy the engine. A chain, properly lubricated, lasts the life of the engine. Toyota eliminated that entire failure category. When Ford tore down a high-mileage 4A in the early 1990s, the internal report said the wear was inconsistent with the mileage. The engine looked newer inside than the odometer suggested. That report directly influenced Ford's Zetec development program. Honda found evidence of generations of quiet, incremental refinement, not revolutionary breakthroughs, just relentless improvement. Each generation slightly better than the last. Neither Ford, Chevrolet, nor Honda had institutionalized that philosophy the same way. And it was producing results they could not ignore. Here is the part that automotive journalists almost never discuss when they talk about why Toyota Corolla engines last so long, and it might be the single most important factor of all: the lubrication system. Every internal combustion engine has an oil pump that pressurizes oil and forces it through passages to lubricate the moving parts. The engineering decisions around that system, where the oil goes first, how much pressure is maintained at different RPM levels, how quickly oil reaches critical components on a cold start, how the system behaves when oil level drops slightly below optimal, are decisions that have enormous long-term consequences for engine wear. Toyota over-engineered the oiling system in the Corolla's engines in ways that competitors considered unnecessary and expensive for a vehicle in this price class. The oil passages leading to the main and rod bearings in the 4AFE and its successors were sized larger than the minimum required for adequate lubrication. Why does that matter? Because larger passages mean lower oil velocity for the same flow rate, which means less turbulence at bearing surfaces, which means a more consistent oil film thickness under the bearing. A consistent oil film is what separates metal from metal. It is what prevents wear. Toyota made that film more reliable by giving it more room to flow smoothly. The cold start behavior of the Corolla's oil system was also engineered differently from competitors. In the first seconds after a cold engine start, before oil pressure fully builds, is when the majority of engine wear in any internal combustion engine occurs. Toyota positioned the oil pump pickup and the critical bearing galleries to minimize the time between startup and full oil pressure at the most wear-sensitive components. In practical terms, the Corolla's engine reached protective oil pressure faster on a cold start than most competitors in its class. None of this shows up in a brochure. None of it affects the horsepower number or the fuel economy figure or the price sticker. It is invisible engineering that only reveals itself over 200,000 miles of daily driving. And that is exactly where Toyota wanted it to show up. When Chevrolet's engineering teams did teardown analysis on high-mileage Corolla engines during the late 1980s and compared the bearing wear patterns to their own comparable engines, the difference in bearing surface condition at equivalent mileages was significant enough to generate serious internal discussion about why it was happening. The conclusion that came out of those discussions contributed directly to the revised oiling system specifications that went into several Chevrolet four-cylinder programs in the early 1990s. Toyota changed how their competitors built engines not by publishing their methods, but by building engines so good that their competitors had no choice but to figure out what they were doing. No story about the Corolla engine is complete without honesty about the one generation where Toyota got it wrong. In 1999, Toyota introduced the 1ZZ FE engine in the 8th generation Corolla. On paper, it was everything Toyota's engineering reputation promised: lightweight aluminum block, variable valve timing on the intake cam, excellent fuel economy, clean emissions. The 1ZZ FE looked like the logical evolution of everything Toyota had built in the previous 3 decades. It had one serious problem: oil consumption. The 1ZZ FE used piston rings that were designed with very low tension to reduce internal friction and improve fuel economy. Lower ring tension does reduce friction, and it does improve efficiency in a measurable way. But it also makes the rings less effective at preventing oil from migrating past the pistons into the combustion chamber. And in the real world, with the normal variations in driving style and maintenance habits that Toyota's original engineering brief had always accounted for, those low-tension rings allowed oil consumption rates that were unacceptable for a Toyota product. Owners reported consuming a quart of oil every 1,000 to 2,000 miles in some cases. Not because the engine was failing in a traditional sense, because Toyota had prioritized efficiency over the oil control that had always been a cornerstone of their reliability formula. This was a significant departure from the philosophy that had made the Corolla's engine legendary, and the market noticed. The 1ZZ FE generation became the most complained about Corolla powertrain in the vehicle's history up to that point. Toyota's response was notable. They did not issue a sweeping recall. They did not fully acknowledge the extent of the problem publicly in the way many owners felt they should have. But internally, the lesson was absorbed completely. The engineers who had signed off on those low-tension rings had to answer for it. And when Toyota developed the replacement engine, the 2ZR FE, that arrived in 2008, oil control was treated as a non-negotiable priority, even if it cost some efficiency. The 1ZZ FE generation is a chapter in the Corolla story that Toyota would rather not lead with, but it matters because of what it reveals about what happens when the core philosophy gets compromised. The one time Toyota traded their reliability formula for an efficiency metric, they paid for it in owner satisfaction and brand trust. They have not made the same trade since. If the 1ZZ FE was Toyota's mistake, the 2ZR FE that replaced it in 2008 was the correction. And the correction was so thorough, so deliberate, and so clearly informed by what had gone wrong, that automotive engineers who analyzed it called it one of the most purposeful engine redesigns they had seen from a mainstream manufacturer. Toyota did not just fix the ring tension problem. They rebuilt the entire engine around a reinstatement of the original Corolla engineering philosophy. Reliability above all else, with efficiency as a secondary goal rather than the primary one. The 2ZR-FE used a new die-cast aluminum block with different alloy specifications chosen specifically for improved thermal stability and dimensional consistency across a wide range of operating temperatures. What that means in practical terms is that the cylinder bores maintained their geometry more precisely as the engine heated up and cooled down through daily driving cycles, which directly improved ring seal consistency and oil control. The piston rings went back to higher tension specifications. Fuel economy suffered slightly compared to what Toyota could have achieved with low-tension rings. Toyota accepted that trade. The reliability philosophy had been re-established as primary. The valve train in the 2ZR FE used Toyota's dual VVT-I system, which applied variable timing to both the intake and exhaust camshafts independently. In earlier engines, Toyota had only variably timed the intake cam. Adding exhaust cam timing control allowed the engine to optimize combustion efficiency across a much wider RPM range, which reduced heat generation and internal stress at partial throttle conditions, which is exactly where most real-world driving happens. The timing chain returned, as it had been in the best Corolla engines before the 1ZZ FE. No belt to replace. No catastrophic failure mode if a service interval was missed. The chain, lubricated by the same oil that flows through every other bearing in the engine, either gets changed with the oil or it outlasts the car. The results were immediate and have only improved with time. The 2ZR FE generation Corollas began accumulating the same kind of forum legend status that the 4AFE had earned before it. Owners posting 200,000-mile photos, then 250,000. Then 300,000. Independent mechanics reporting that they rarely see these engines come in with serious internal problems. Taxi fleets in markets where the Corolla is a working vehicle reporting service lives that other manufacturers cannot match. Ford benchmarked the 2ZR FE during its development of the Dragon engine series. Honda referenced the thermal management and ring seal specifications when engineering the L15B that went into the 10th generation Civic. Chevrolet's Ecotech program team was well aware of what Toyota had built and what it was costing them in conquest sales. The 2ZR FE is, by the honest assessment of most automotive engineers who have studied it, one of the finest mass production engines of the modern era. Not because it is the most powerful, not because it is the most technologically advanced, because it does what the very first Corolla engine set out to do in 1966. And it does it better than anything Toyota had built before it. I have referenced several times in this video that Toyota's competitors analyzed Corolla engines, ran comparison studies, and modified their own programs in response to what they found. I want to be specific about what that actually looked like, because it is more significant than most people realize. Ford's response to the Corolla threat was not a single event. It was a decade-long evolution of priorities that you can trace through the engineering changes in their compact car lineup. In the late 1980s and through the 1990s, Ford's four-cylinder engines for the Escort and later the Focus were benchmarked directly against Toyota's units. The Zetec engine that Ford introduced in the mid-1990s incorporated bearing clearance specifications, timing chain design philosophy, and oil system geometry that engineers who had previously worked at Toyota suppliers have publicly described as clearly influenced by Toyota's approach. Ford will never say they copied Toyota. They do not need to. The engineering record speaks for itself. Chevrolet's situation was more complicated because General Motors' organizational structure in the 1980s and 1990s made it harder to implement the kind of rapid, focused engineering response that a more centralized company could execute. But the Ecotec four-cylinder engine program, which became the foundation of GM's small car engineering for 2 decades, was developed with explicit competitive benchmarks against the Corolla's powertrain. GM engineers have said in interviews that the Ecotec program's emphasis on long-term reliability over peak performance numbers was a direct philosophical response to what Toyota had demonstrated was possible and what the market was demanding as a result. Honda's response is perhaps the most interesting because Honda and Toyota represent the 2 dominant philosophies in Japanese automotive engineering. Honda's approach has always been performance-forward, technically ambitious, and willing to accept some reliability trade-offs for engineering sophistication. Toyota's approach has always been reliability first, long-term ownership cost above all else. The Corolla's engine data forced Honda to take a harder look at whether their philosophy was leaving competitive vulnerability on the table. The VTEC system that Honda developed and the engineering refinements that went into their D-Series and later K-Series engines showed clear evidence of reliability-focused changes that Honda's engineers acknowledged were partly in response to customer feedback about how their products compared to Toyota's in long-term ownership surveys. Honda never fully adopted Toyota's philosophy. They are too proud of their engineering identity for that. But they moved toward it in specific, measurable ways.